In this lecture, we are going to talk about quadratic optimization. So basically, our goal is to determine a closed form solution that can be used for quadratic minimization problem with equality constraint. The reason that we are doing this is because most of the real-world problems could be represented as quadratic optimization. Or after some linearization and relaxing some of the constraints, we can reformulate them as quadratic problems. So here is the generic form. We define vector of variables as vector y, which includes y1, y2, ym. So we have m variables. We define C to be a symmetric, positive, definite matrix. We define A and m by n matrix. F has n elements. So here's how we formulate the problem. Our objective function is 1 over 2 y transpose vector of variables C, which is an m by m matrix y minus b transpose y. B is also a vector of coefficients. So the only variables here are y's. Y's are our unknowns. And what is our equality constraint? It's A transpose y, which is vector of variables, is equal to f. So again here, y is the only unknown or variable. Linear equality constraint. So let's rewrite our optimization problem. Our problem is minimizing 1 divided by 2 y transpose cy minus b transpose y. Y is the variable subject to A transpose y is equal to f, where C is m by m, is positive definite matrix. A is m by n matrix with rank of n, and we assume m is greater than or equal to n. What does that mean? Number of variables is more than number of constraints. Because if you remember, if number of constraints is more than number of variables, then our problem is over constrained, which means we can either find one solution or there is no solution. Further, b and y both are vectors of m dimensions, column vectors, and f is a vector of n dimension, again a column vector. So as the very first step, we do what we did in convex optimization. We define lambda 1 to lambda n. This corresponds to constraint 1 to constraint n. Each of these lambdas are the Lagrange multipliers. Then we define the Lagrange function as a function of variables and Lagrange multipliers. So it's going to be our objective function plus vector of Lagrange multipliers multiplied by our equality constraint. So if we simplify this further, like these two can be grouped together. So our Lagrange function is going to be half of y transpose cy minus b minus a lambda transpose y minus lambda transpose f. So how do we have this a lambda? So this is going to be lambda transpose A transpose, which is equal to A lambda transpose. All right. In the next step, so this was step 1, step 2. The next step, we write the KKT conditions, which are derivative of lambda with respect to y's, which is going to be 2 multiplied by over 2 cy minus b minus a lambda. So if we simplify this further, these two cancel each other, we are going to have cy plus a lambda is equal to b. This is one equation. And then we have derivative of lambda with derivative of Lagrange function with respect to lambda, which is nothing but our equality constraint. A transpose y minus f is equal to 0. So A transpose y is equal to f. So basically, we have a set of linear equations, and we want to find the answer to this set of linear equations. I'm going to represent these two in terms of matrices. So what we are going to have is C, A transpose 0. These are all block matrices. So this is a block matrix 0. We have vector y, vector lambda is equal to b and f. So the matrix for this system is symmetric. So what we are going to do, we try to remove y from the first set of equations. So let me rewrite this in the next page. We have C, A transpose 0, y lambda, bf. All right. So we start with the first row. We have cy plus a lambda is equal to b. Then we bring this to the other side. We have cy is equal to b minus a lambda. We multiply this by c inverse from the left side. So we have y is equal to c inverse b minus a lambda. So we have y in terms of lambda or our Lagrange multipliers. Now we are going to replace this in the second equation, which is A transpose lambda is equal to F. So we have A transpose C inverse. Oh, we have A transpose Y is equal to F. So we have A transpose C inverse B minus A lambda is equal to F. We simplify this further. Let's see what happens. So have A transpose C inverse B minus A transpose C inverse A lambda is equal to F. What we want to do, we want to keep this one at one side and the rest of them, which are constant, at the other side. So we have A transpose C inverse A multiplied by lambda is equal to A transpose C inverse B minus F. So this is all we have till this point. So lambda is our Lagrange multipliers vector, which is our unknown variable here. So now the question is, what's the guarantee that this matrix is invertible? Because we already know that C is invertible. But here's the thing. We know that C is symmetric, positive, definite. So C is symmetric, positive, definite. We also know that columns of A are linearly independent. So that leads to having A transpose C inverse A is symmetric, positive, definite. And ultimately, we can conclude that it's invertible. So there is an answer to this equation. So given this, we can find lambda. So lambda is equal to A transpose C inverse A inverse multiplied by A transpose C inverse B minus F. And then we insert this in equation star. Y is equal to C inverse multiplied by B minus A lambda. So as you can see, we could determine a closed form solution for the variables of this quadratic optimization problem. There is an equivalent system of equations for this. Let's define E to be B minus A lambda. So given the simplifications that we did in the previous slide, we have C, A transpose 0, Y lambda is equal to BF. So if we assume that definition, this is equivalent to the system E is B minus A lambda, Y is C inverse E, and A transpose Y is equal to F. So these two are equivalent. And the second one is called equilibrium equations and defined by the strand. So this is some sort of something that I would like you to do. Go back in this video and try to write down the steps to determine this closed form solution. So now what we are going to do, we are going to solve an example for quadratic program. Here's the question. Minimizing y1 squared plus y2 squared divided by 2, y1, y2 are our variables, subject to 2y1 minus y2 is equal to 5. So in the very first step, we have to find the elements for our standard representation, the representation that we defined in the first slide. So what was the standard format that we used? We used minimizing 1 over 2 y transpose c y minus b transpose y, y, subject to a transpose y is equal to x. So here c is going to be 1 0 0 1, b is 0 0, because we only have the quadratic terms, we don't have y1 or y2 with power 1. A is going to be 2 and minus 1 because we only have one constraint. So let's look at the dimensions, 2 by 2, 2 by 1, 2 by 1. And f is going to be 1 by 1. F is simply 5. So this is our f. These are the coefficients of A, and the objective gives us C. So this is the matrix representation. We have C, we have A transpose, 0, y1, y2, lambda. We only have one lambda because we only have one constraint. Is equal to BF. So if you replace the numbers, we are going to have 1, 0, 2, 0, 1, minus 1, 2, minus 1, 0. I'm going to show the blocks so you can notice how we created this matrix. y1, y2, lambda is equal to B is 0, 0, and F is 5. So if you solve this set of equations, this is going to be your answer. y1 is going to be 2, y sub 2 is going to be minus 1, and lambda is going to be minus 1. So there is another representation for quadratic optimization problem, and this time we don't show the equality constraint. So let's define if A is an invertible symmetric matrix, then the function f of x. Now we use A instead of C. We don't have any constraints. X transpose B. This one has a minimum value if and only if. So this means if and only if A is positive semi-definite. In this case, the optimal value is obtained for a unique value of x. Obtained for a unique value of x, namely x star, and we have, so here's what we have. The optimal value x star is going to be minus A inverse multiplied by B, and the value of our objective function f sub mean at x star is f evaluated at a minus 1 A inverse B, which is minus 1 over 2 B transpose A inverse B. So this is our optimal value of objective function. Optimal value of objective function. So in this lecture, we talked about quadratic optimization. We studied two scenarios: linearly constrained problem as well as unconstrained problem. We also solved an example of linearly constrained quadratic optimization problem.